Now let's talk about volumes. Before we can actually start working with volumes, we should have a good understanding about what they are. To help us understand what volumes are, think of an image. An image is basically a 2D grid made out of pixels. Each pixel stores a different RGB value, and everything put together will represent something. Now, a volume is nothing more but a 3D grid made out of voxels, and each voxel is going to be storing different types of information, and that can be used to represent many different things. Let's say we have an object, and we want to represent this object as a volume. Just like in an image, you would need a higher resolution to have more detail on your image. On a volume grid, you will need a higher number of voxels to have an accurate representation of the object. So if we change the size of the voxel, if we lower it, we can get more detail. If we increase the size of the voxel, we will have a less accurate representation of the object. Let's put this back to 0.05. Inside Houdini, you have two different types of volumes: standard Houdini volumes and OpenVDB volumes. This is a standard Houdini volume. Let's have a look at how many voxels we have here. This is a fog volume, and if we middle mouse button here, we'll see that we have a primitive named density representing our volume. This is our density volume, and this is the resolution on X, Y, and Z, and the total amount of voxels that we have, 65,000 in this case. If we switch over to an OpenVDB volume, we'll notice a slight difference, a slight change in the viewport, but what you'll notice is that OpenVDBs will have a much lower number of voxels. The reason for that is because OpenVDBs are also referred to as sparse volumes. They're optimized in order to save memory and calculation time. What they do is they ignore all the areas where the voxels are empty, will be discarded. What you're seeing here are the areas where information is actually being stored. Everything else is being discarded. Even though the bounding box for the volume is this, we're not storing information all over. Volumes can be used to represent scalar fields, like this one, where each voxel stores a float value of density. They can be used to represent vector fields, something more like this, where each voxel is storing a vector value, and that vector can then be translated. You can slice the volume to have a look at this is just cutting one slice of the volume, and the RGB values are showing us the XYZ values of the vector. And then we can this is actual geometry. We have points here, and we can volume trail those points by having a look at the trail that each one of these points would make if it was displaced, if it was advected by that volume, that vector field. And this is how we usually have a look at vector fields. The third type of volume that you can have is a signed distance field. And signed distance fields will look something like this. You have the standard Houdini volume version, and you also have the OpenVDB version. Essentially, what an SDF or a signed distance field stores is each voxel is going to store the distance to the closest point on the surface. On the case of standard Houdini volumes, you'll have positive values for the voxels that are inside that surface, and you'll have negative values for the voxels that are outside. The mesh representation that you see is where you have values of 0. In the case of an OpenVDB signed distance field, it'll be exactly the same, with the difference being that on an OpenVDB SDF you will have negative values inside and positive values outside. So now that we know a bit more about volumes, let's move on to start experimenting with them.